Okay, great. So today's talk is dedicated to at least start reviewing the content of the proof itself of MIP star is equal to RE. Before we go that way, we will finish our discussion from last time about Cohn's embedding problem. Okay, maybe I'll do that. Didn't work. Great, so we start with finishing the discussion about Cohn's embedding, and then I will introduce the main theorem of the paper MIP star is equal to RE, which is called the compression theorem. Many things are called compression, but it is a good name for this theorem, so I'll keep this name. And I will show that if you know that the compression theorem is true, you can deduce that RE is contained in MIP star. So you prove the hard part, like the essence of the paper. And since this just from this theorem you can deduce what you wanted, it's understood that this is a hard theorem. So there are many ingredients in proving this theorem. So I'll start and review these ingredients clearly in the bit of a hand wavy way, but with some or most of the interesting details, hopefully. And this will be the end of this talk and the next one probably. So we will go through these three parts that are mentioned here during the end of this talk and the next talk. And that's for now. And then maybe at the end of this talk, I will talk a bit about what will happen after we review this proof. Great. So let's dive in. So we go back to Cohn's embedding problem. So I want to give you a few reminders. So we defined what's called hyperlinearity last time. So we had this finitely presented algebra. So this was a quotient of the free star algebra generated on the elements x1 up to xk. So these are non-commuting polynomials in x1 up to xk and x1 conjugate up to xk conjugate. Modulo these relations f1 up to fr. And we said that such an algebra is hyperlinear if there exists two things. First of all, a function, delta, from the algebra to the non-negative real numbers that only sends 0 to the 0 number, and all non-zero elements are sent to strictly positive real numbers. And also there exists some constant m, such that for every finite set in this algebra in U, with representatives from the free algebra G tilde, so just taking some section of these elements, some inverse image inside the free algebra. So if we have these two things, and for every epsilon greater than 0, there exists an epsilon representation, A1 up to AK, such that if you take the difference between G tilde and G tilde prime, and you this is a polynomial, so you just need to put in the elements A1 up to AK. These are matrices, so we have a polynomial of matrices. So this is some matrix. So this is a matrix. So it has a Hilbert-Schmidt norm, which is just this normalized 2 norm that we talked about last time. And we want this Hilbert-Schmidt norm to be bounded from below by this function on the difference between G and G prime. And also we want all of our epsilon representations to be bounded by this number M. Okay, all the elements of the epsilon representation. So if you don't remember what an epsilon representation is, an epsilon representation is just this kind of a tuple. So A1 up to AK is an epsilon rep if fi of the vector A1 up to AK, the Hilbert-Schmidt norm of it is just bounded from above by epsilon. And this is for any I between R and 1. So all of the relations are almost satisfied. Okay, epsilon satisfied. Great. So this was hyperlinearity, and I claimed last time.
Michael, remind me, we choose the representatives in advance or
okay,
after?
so you can think I could have just chose beforehand for any element a representative in the algebra, and actually this I will use this fact that I can choose beforehand, not for any finite set. I also choose representatives, but actually, at least in the way I presented it now, it doesn't matter. Okay. Cool. And now I'm claiming last time I claimed that
so
it's
we only
if and
work
only
with
if.
the representatives. Michael, this means that the G's themselves mean nothing. It's just the G tilde that. Sorry. No. Delta is defined.
That,
sorry. Delta is defined.
The delta is defined on you. Right.
Sorry. Yeah.
Okay. Yes, Alon.
Yes, I'm sorry also, but shouldn't this constant m depend on f? I mean, you can scale.
I just said that there exists some m that no, it doesn't depend on f. Why? It depends on the f1s up to. It depends only on you. The constant m depends only on you.
But if I take some element and scale it, like it's an algebra, so I can scale things linearly.
But I wrote that you need only to bound the image of the generators alone.
Okay, so my mistake.
Yeah. So okay, this is a good point. Notice that the thing I bounded using m is just the operator norm of the image of the generators of the algebra U. Okay, this is what I bounded. Okay, great. So last time I claimed that being hyperlinear is the same as embedding into this algebra, this scary looking algebra, the bounded product of the M and IC, so of matrix algebras, countable bounded product. So these are sequence of algebras, of matrices. And we take the quotient with respect to the ideal generated by all sequences with a Hilbert-Schmidt norm of the sequence having limit 0. Okay, so
can I ask
yes.
Can I ask another technical question, which continues the others? So what if these G's that generate, these generators, I pick them to be huge in some sense? Then
A1 up to AK?
I would, what?
A1 up to AK? The generators are sent to A1 to up to AK. You ask what happens if I can separate points, but using larger and larger elements?
What do I want?
The G's can have the G's can have very large operator norm. The only thing I'm asking you is that the generators have some uniform bound on their images in all epsilon representations. So all separating epsilon representations are taken such that the image of the generators is bounded in the operator norm with some uniform bound. So it's this M. And this M depends only on the algebra U. It doesn't have to be one. So we had a small discussion last time. Maybe one will always suffice, but this is just not true. And I gave an example, but I assume that there is such a bound. Okay. Now you can see that if you have such a bound on the generators, you can deduce, because the operator norm is submultiplicative, and you have the triangle inequality, you can deduce some, for any specific G, you can deduce some bound on its operator norm, right? But the point is that, what? Nothing?
Can I try something? I mean, it's similar enough to things that I've seen and done. So let me perhaps say how I view it, because I think for me, it's very convincing. You want to have epsilon representations for every epsilon small. Now, there are two ways in which you can cheat.
That separates all finite sets.
Separates all finite. No, I want stronger than yeah. The first cheat, there are various cheats that you can do. You can not separate. Not good. We're not letting you do this. You can cheat by taking the representative DAs, the images, very, very small. And by this make all the difference. But that we allow you, that we forbid by throwing in this delta condition. And then you can cheat by making them huge, and that we forbid by putting this big M. So there is the basic condition. There are two obvious ways to cheat about this, and then you block them. This is it.
Great, thanks, Nadi. So I'll move along, okay? Because I think we had a bit of this discussion last time, and I think for now, let's just take this definition as a given. We gave it, now Nati gave even more motivation on any part of the definition, every part of the definition, but let's move along. Okay, so last time I just stated that U is hyperlinear if and only if it embeds in this algebra, which is this algebra of sequences of matrices, such that the sequence is uniformly bounded by some constant, and this constant depends on the specific sequence in the operator norm. And my claim is that the set of all sequences whose Hilbert-Schmidt norm tends to 0 is an ideal inside this thing. So this quotient is an algebra, and being hyperlinear is the same as embedding in this algebra. Now, I didn't prove both parts. I proved only that if you are hyperlinear, then you embed in this algebra, and this is the only part. The other part is actually easier, but let me just prove it again, because last time we had some, we stayed for about 20 minutes after the talk to review this proof. So really quickly, I want to state some things that will repair the bad things that I said last time. Okay, so first of all, let's, for our ease, just assume that delta is continuous. Continuous in what sense? This U is a vector space with a countable basis. Okay, so you can easily define an L1 norm over this vector space. And with respect to this L1 norm, I assume that this delta is continuous. So you don't actually need it, but the proof becomes much clearer when I do that. So you can think of it as if I used it as part of the definition of hyperlinearity, but probably anyone in this audience can fix it and just drop this assumption. Now I want to stress that there is a short exact sequences of vector spaces. Okay, so this is a short exact sequence that defines the algebra U. Okay, but we can just forget about the fact that it has the product structure and just think about the ideal that we took as a quotient as a vector space, C star of x1 up to xk, the free star algebra, and U just as vector spaces. And then there's a section, you can take an embedding of U inside this free algebra, which is an embedding as vector spaces. This is no longer an embedding as an algebra, but now at least it is closed under addition and scalar multiplication, which was a bit of that was a point that at least disturbed me last time. What happens when you take sums of such inverse images and so on? So take this section such that this is an embedding as vector spaces, and this is possible because all vector spaces are projective. I think this is the correct way to state this phenomenon. And now you have this U prime. Okay, so now this U prime is a sub vector space of the free algebra, and this is a sub vector space which represent each element of U. So every element of U as a single representative in this U prime. Now take U double prime to be the span of the basis of U prime with respect to the field Qi, where Qi is just, we talked about it last time, so Qi is just all the A plus Bi's such that A and B are rational. So this is a field, and we can take the span with respect to this field. And in the L1 norm that I mentioned a moment ago, this is dense inside U prime. Okay, so when I try to say that you can take a dense subset, you can take this specific subset, for example. Now I want you to know the following thing. If you take a vector of matrices, so some sequence of matrices, K matrices, and you take two elements inside U prime, okay, so every element inside U prime is a linear combination of a finite subset of the basis, right? So F is sum of alpha I V I, and assume that F and G are represented using the same elements of the basis. This is without loss of generality. Then I want to bound from above the difference in their Hilbert-Schmidt norm using only the coefficients. So how do I do that? My claim is that if you input the tuple A1 up to AK inside F, this is just a polynomial, right? F is a polynomial and G is a polynomial. So you can put inside F A1 up to AK, put inside G A1 up to AK, you get some matrix. You can take the difference of these two matrices. You take the Hilbert-Schmidt norm of these two matrices. By the triangle inequality and the fact that the operator norm bounds from above the Hilbert-Schmidt norm of a matrix, and the fact that the operator norm, okay, so I don't even need the fact that the operator norm is submultiplicative. I think that I don't even need that. But if you want, you can say something about this. You don't need, but if you want, you can say something about this number, the maximum over VIA op for all the VIs. Notice that this is a finite set of VIs. I don't take all the bases. I take only the elements that appear inside these linear combinations of F and G. The point is that you can bound it using this number M from before, potentially, if you know the degree and the complexity of all the VIs, but this is not necessary here. This is just some number, okay? The maximum operator norm of this, and you can sum up the differences of the coefficients alpha and beta I. So these are complex numbers. You take their absolute value and take their sum. And my claim is that the Hilbert-Schmidt norm of this thing is bounded by this thing. Great, so this is just basic linear algebra and the fact that the operator norm bounds the Hilbert-Schmidt norm. And from that, you can deduce the following. You can see that the Hilbert-Schmidt norm.
Michael, you know, if you want to just run over this, that's fine, because it's about.
Okay, so stop me if something is not clear. Yeah,
no,
let's
there isn't really, I think, of this inequality. I mean, the operator norm of a matrix times the norm of a vector, that's the definition of an operator norm. It's at least as big as the norm of the image of the vector.
But what is the vector here? The alpha I minus beta I is just the coefficients in the polynomials.
No, think of them as this is a vector whose ith coordinate is alpha I minus beta I.
But this is not the way I think of it. You have here a matrix. The point is this is a matrix, okay? Yeah, but okay, so.
I think so.
Okay.
So I haven't really checked, but it seems like this inequality like this couldn't be anything but what I just
okay,
said.
so I'm sure that you can understand why this is true. So Nati, you have your way of seeing this. I see it just as application of triangle inequality and the fact that the operator norm bounds the Hilbert-Schmidt norm. My claim that you can take these two facts and just deduce this thing, and you say that there is maybe a way using the definition of an operator norm.
Let me say just one small thing that you know, I'm not sure everyone has it in their mind. The operator norm of a matrix or an operator is just how much the length of a vector increases by applying this linear function. That's all. And this is the meaning of the operator norm. If you think about it this way, then I think this should be completely obvious.
Okay. Okay. But I do want to move along, Nati, at least for now. My claim is just that the Hilbert-Schmidt norm has the triangle inequality. So you can check that the fact that I claim that this thing is strictly smaller than this thing implies automatically that this thing is bounded from below by the Hilbert-Schmidt norm of the GA minus this number. And I call this number epsilon G because this number, I think of F as something fixed and of the G as something that I vary. And then the claim is that the norm of F is bounded by the norm of G minus some epsilon that depends only on this G. Okay, so these two things depend only on the G. Okay, so now what we want to do, so the U double prime is a countable set. So we can take an ascending sequence.
Why do you say this thing depends only on the G, where the alpha I depends on F, no?
Yeah, but I fix F, okay? So I think of F as something fixed and I vary the G. So you want the F as being fixed outside the things that I separate, and you want to approximate it using G's that actually are separated using the epsilon representations that I take, okay?
Yeah.
Great. So first of all, take U double prime to be so take an ascending sequence of finite sets that whose union is U double prime. For any f that lives in U prime and does not live in U double prime, a priori, if I take for any fi, so for any fi, take an 1a1 1 over 2 to the I rep that separates it. Okay, so I have here now a sequence of epsilon representations such that the epsilon tends to 0 and the FIs are separated, like the FIs get larger and larger and they separate more and more elements out of the set, out of the vector space U double prime. And the point is that now I want to say that even if you are not in U double prime, if you are only in U prime, you are still separated using this sequence of epsilon representations. Okay, so let me explain why this is true. And this will explain why this is an embedding. So, okay, what is this? So you take these I epsilon representation. So let's call each one of these epsilon representation, oops, AI vector. Okay, so an epsilon representation is just a vector of matrices. So AI vector is just the ith epsilon representation. So I will just send any element of U to the sequence FAI. I goes from 1 to infinity. And I claim that this is actually an embedding into this sequence of matrices algebra. Okay, great. And now the fact that it is the fact that it is a homomorphism of algebras is something that one needs to check. Okay, and I will not check it now. It comes out of the fact that these are epsilon representations and the fact that we modded out by this sequence of all sequences that tends to 0 within the Hilbert-Schmidt norm. I'm only going to concentrate on the fact that it is an embedding. Okay, so why is this an embedding? Because any element that is, so for any element in U double prime, this is clearly an embedding because this sequence from some point onwards, the Hilbert-Schmidt norm of the image of any element from U double prime is bounded from below by delta of this element, which is strictly larger than 0, so it doesn't tend to 0. So this is why any element in U double prime is separated from 0. Now we need to explain why any element in U prime that is not in U double prime is also bounded away from 0. And the way you see that is that you can take a sequence of GNs inside U double prime that tends to this F. So we take this GN such that epsilon of GN tends to 0. So this number goes to 0, which is exactly saying that the L1 distance between the GNs and F tends to 0. You can check that this is the same thing. And as well, since we took delta to be continuous, this is the same. We automatically get that delta GN tends to delta F. Okay, but this fact means that when you go further in the epsilon representation, so without loss of generality, we can assume that GI lives inside FI. Okay, so this F, we just showed that the Hilbert-Schmidt norm of F is bounded away by this Hilbert-Schmidt norm of G, which is strictly larger. So if this is GI, this is strictly larger than delta GI, minus some epsilon of GI that tends to 0. And so this thing tends to delta of F, this thing tends to 0. So we bounded our sequence, the lim inf of our sequence below, from below by delta of F, which is strictly larger than 0. So we are bounded away from 0. This is not a sequence that tends to 0. Hopefully, this closed a gap that we had last time. I don't think we should talk about it anymore because we want to get it in the first hour, finish our discussion on Cohn's embedding problem, and in the second hour, start our discussion about the proof, the MIP star is equal to RE proof. So I'll recall some things that we talked about also last time, because it's important in a moment. So I didn't like the fact that we had many indices. So we had these ni's. We didn't have this product of the same matrix, the same algebra. So the way we can fix that is that we take the direct limit of matrix algebras of power of 2, of dimension, which is a power of 2. And we said that you can just replace all these m and i's by this r naught. Okay, so we call this direct limit r naught, and every epsilon representation into some m and I is a 2 epsilon representation. For example, this 2 is just quite arbitrarily, you can take any constant which is larger than 1, representation into some power of 2. And the separation of points gets ruined, so the delta is divided at most by 2. So we don't actually lose anything regarding hyperlinearity when we replace the m and i's with this r naught. So now I'm claiming that our previous proof just proves that being hyperlinear is the same as embedding in this thing. And the reason that we wanted this r naught is because there is this notion of a trace over this r naught. So the direct limit of these matrices has the notion of a normalized trace, and thus has the notion of a Hilbert-Schmidt norm. But it doesn't mean that every sequence, so we had this point that not all sequences of matrices have a limit of their traces. So you can take the trace of any element in R naught. So any element in R naught has a trace, has a normalized trace, but it doesn't mean that any sequence of such have a limit. And the way to fix that is some magic called non-principal ultrafilters and ultralimits. So you just fix this magic black box called a non-principal ultrafilter, and then every such sequence automatically has now a limit, which is called the ultralimit. And now there is a reasonable way of defining a trace over this algebra. So this is now an algebra with a well-defined trace over it. Okay, and this trace is the ultralimit of these traces. And now I claim that being hyperlinear is the same as being embedded in the sequence of elements in this sequence of elements. But when I care only about the inputs in the ultrafilter, so instead of modding out by sequences whose limit in the Hilbert-Schmidt norm is 0, I now mod out by elements whose ultralimit is 0 in the Hilbert-Schmidt norm, whose Hilbert-Schmidt norm ultralimit is 0. Great, and we call this R naught the ultra power of R naught, metric ultra power of R naught actually. And okay, so we had this algebra, and the problem is that, at least for now, this algebra doesn't live inside the bounded operators of any Hilbert space. And we want to fix that point as well. We want to think of this algebra as embedded inside the bounded operators on some Hilbert space. So the space R naught acts naturally and faithfully on the sequences, on complex sequences that are square summable, okay? And thus it embeds in the bounded operators of this L2, which is a Hilbert space. And there is a way to extend this action such that sequences of elements from R naught act on sequences of elements from L2, okay? So if you take this action, you get an action of R naught U on some non-separable Hilbert space, okay? Some ultra power of these L2s. And this means that this R naught U already embeds in some bounded operators on some Hilbert space. Okay, great. So we have this R naught U, which is embedded in BH, and there is this weak operator topology, which is a very important topology on the bounded operators of a Hilbert space. And we would like this algebra to be closed under this topology. Okay, so we just take its closure. This is sometimes called the von Neumann closure.
Michael, just a second. When you took this ultra product of L2s, it was L2s of a finite dimensional L2 each time that you take ultra product of them?
Ultra power?
Ultra power, it's ultra power of the infinite dimensional infinitely many time, or you take for every n, every two to the n, you take a finite dimension, and you take ultra product of these finite dimensional ones.
I think I do it to the L2 itself, to the infinite thing, but I didn't prepare this part.
Why do you have to do it? I mean, why not?
Maybe I cannot do it. Maybe I can do it in another way, Alex. But Alon, okay, maybe Alon will say something. But the main point is that you can embed this algebra inside the bounded operators on some Hilbert space. Alon, do you want to elaborate?
I think if you take the ultra product of this finite dimensional, I think it's already an Hilbert space. That's what I want to say.
Yes, but Alex, the point is that he wants to talk about what the ultra power of R naught acts on. Like R naught doesn't act on finite dimensional Hilbert spaces. It only acts on.
I know, I understand, but I think that R naught is acting on the ultra product of infinitely many Hilbert spaces where each one of them is finite dimensional.
I think you are correct, because probably if you take an ultra product of finite dimensional spaces with unbounded dimension, then it probably the Hilbert space Michael constructed.
No, not bounded. I didn't say bounded dimension. I just
unbounded.
I just wanted to say that to think about. I mean, if it's correct to think about it in the following simple way, this R naught is basically a product, ultra product of n by n matrices, not n by m by n matrices with m is 2 to the n, and n goes to infinity. Now each one.
Alex, maybe it's true, but it's a bit circumventing my point. Okay, so maybe you have a smaller Hilbert space where you can embed your algebra in the bounded operators on it. But at least for now, let's not care about the specific Hilbert space that we embed our algebra in. Okay, so the bounded operators of which Hilbert space?
Don't you need this space to be non-separable?
I claim that the way I built it, it's not non-separable. The way
I
Alex built it, maybe it is.
I think the way I suggest to build it is separable, no?
Yeah, so
this is what I'm asking.
But my point is that I don't care. So my only thing that
isn't it essential for you, Michael? Isn't it essential for you that it be non-separable?
No, it's not essential. What Alex said, if it works, it's great. But the point is just I wanted to embed it. So I just wanted some faithful representation of my algebra, okay? And I claim that this is a way of constructing a faithful representation of my algebra, and maybe there is an easier way. So Alex is claiming that there is maybe a potentially easier, or at least nicer, in the sense that it gives you a separable Hilbert space. But at least for now, I don't want to, I don't really care about this specific point, whether it's separable or not. I just care that you have a faithful representation. So you embed inside some BH.
So just a technical question. When you take the ultra product of the L2, then you reduce to the ones with finite norms, right?
Even bounded.
Bounded, yeah.
Bounded norms, but L2 is already some square summable thing, right?
Yeah, but when you take the ultra product, you might have things with infinite norm.
Yeah, maybe I do need. Okay, so I as I said, like that.
Okay, so
I could have just said
what you want to say is that
confusing. No, maybe this is just confusing.
No,
I could just tell you
without bounded, you will not have a norm on it. I mean, I think you must take the sequences which are of bounded norm. Otherwise, how can you define a norm on them?
Yeah. My point is that probably you are right, both of you. Like Itai's point is it's good, and as Alex said, but I just want you to think of it. Maybe it was bad to even give a flavor of this point, because I just wanted to state that this algebra has a faithful representation. Okay, this was my only point. I wanted to give you a flavor of how can you construct it, but if the details only are only confusing, and the exact way that we do it confuses us, let's just drop it. So claim R naught to the U embeds in some B of H, okay? And there is a way of taking this hand-wavy way of constructing this thing, maybe using the bounded, only taking bounded sequences of sequences, such that this actually embeds in some Hilbert space, in bounded operators of some Hilbert space. Okay, but my point was that when you are already embedded in some bounded operators on some Hilbert space, you can take the weak operator topology, the closure of, with respect to the weak operator topology, and you become what's called the von Neumann algebra. Okay, there is a strictly algebraic way of defining it with no norms at all, but let's not talk about it right now. So you just take this closure with respect to the weak operator topology, and you get some bigger algebra. And this bigger algebra, okay, so here it's called R to the power of U. Okay, I need to open my iPad. Okay, great. So this is R to the U. It has a very famous name. It's a bit of a mouthful, but this is called the ultra power of the hyperfinite. Wow, it writes very slowly. I don't know why. Oops, hyperfinite 2-1 factor. Okay, so this is a very famous name. So if you ever hear about the ultra power of the hyperfinite 2-1 factor, this is this. Okay, and Cohn's embedding problem. Okay, so actually Cohn's embedding problem asks the following: if you have a finite von Neumann algebra, which means if you have a von Neumann algebra, a sub algebra of the bounded operator, so this is von Neumann algebra, lives inside B of H of some H, okay, which is closed in the weak operator topology. Okay, so any subalgebra of B of H which is closed in the weak operator topology is called the von Neumann algebra, and it is also finite, which means it has a normalized trace. Normalized trace. Does it mean that it embeds inside the hyperfinite 2-1 factor? Okay, so we need also separable. Okay, so we assume some topological assumption, but that's it. Okay, so do all separable finite von Neumann algebras embed in this hyperfinite, the ultra power of the hyperfinite 2-1 factor?
In this or in some?
There is only one. They are isomorphic to one another. They are all
isomorphic.
Yeah. This is not trivial, but it is true. Assuming the continuum of points. What do I need to
Who are isomorphic?
There are many ways to construct potentially this R to the U. You can both use different ultra filters, and there are actually other ways to construct it. But up to some natural assumptions, all of them are isomorphic to one another as von Neumann algebras. Right?
So maybe I will say what is the case, but okay, because you assume separable here, you only need to take ultra powers of R whichever, like a countable ultra product. You don't need to take beyond Aleph 0, but you might ask on which ultra filter do we choose? But turns out that these ultra products, like you can choose different ultra filters to take the ultra products with respect to, but these things embed in each other. So for the sake of asking, for the sake of asking whether a von Neumann algebra embeds in one, it's the same as asking whether it embeds in all others. However, to say that all these ultra products are isomorphic is, to show this, you need the continuum hypothesis. So, I mean, this is another discussion on its own, but it turns out it doesn't depend without assuming anything.
Yeah. Can I have a question? Ask a question that relates to what we did so far. So we said that we said that an algebra is hyperlinear if it embeds in. So is it true that if it is hyperlinear if and only if it embeds in R0 to the U?
Yeah, but only if I defined hyperlinear only for finitely presented algebras. And you can check that being embedded in R not to the U is the same as being embedded in R to the U for at least these algebras.
Okay, fine. So the question about being embeddable in R to the U and R0 to the U, this is the same question for finitely
Presented algebras.
Presented algebras. And now,
but it's not the same for finite von Neumann algebras because von Neumann algebras have additional structure, have some like this, they are closed in some topology, so you cannot embed them in R not to the U. You can only embed them potentially in R to the U.
Okay, so but we started with asking a question about algebras. Why are we asking now a question about von Neumann's?
No, so this is the original question of Cohn. Okay, but the actual question that I care about is the in particular that comes next. So we talked only about finitely presented algebras. So my question is as follows. And if you have a finitely presented algebra that embeds in some BH and you don't even need a faithful tracial state. You only need a tracial state. Okay, so you have a finitely presented algebra.
What do you mean by tracial state?
I started saying something about it at just the end of last time. And the point is that you just need to think about the regular trace. Okay, so on matrices, you have this notion of a trace, right? Summing up the eigenvalues. And there is the notion of normalized trace, which is taking the average of the arithmetic average of the arithmetic mean of the eigenvalues. So you have this kind of an analog of this operation, some functional that satisfies some criterions, which generalize this notion of a normalized trace. Okay?
Okay.
Cool. And some algebras have this kind of thing and some others don't. But the point is that if you already embed in R to the U, since R to the U has a tracial state, you can automatically get a tracial state on your original algebra. Okay? So so the fact that so to even assume that you are hyperlinear, so if you want to be hyperlinear, you at least need to assume that you have a tracial state and that you embed in some BH. Okay, so these are just basic assumptions because R to the U have these properties and subalgebras of R to the U inherit these properties. Now the question is, does these two, okay, this is okay? Do these two conditions suffice to being hyperlinear? Okay. If they are not suffice, if they don't suffice, it refutes Cohn's embedding problem. It doesn't prove if this suffices. Maybe there are finite von Neumann algebras that don't come from finitely presented algebras and are a bit more peculiar, that are not hyperfinite, that are not hyperlinear, so they don't embed in R to the U. But you can use the in particular only to refute Cohn's embedding problem, not to prove it.
We don't know a priori that in particular is equivalent. It's just a strict corollary, possibly.
Yeah, exactly. It is a corollary of, right. It's a corollary.
So what you say implicitly, but not explicitly, is that if U is a finite represented algebra that does have these things, it embeds in B of H and it has the tracial state, then it is also closed in the sense that we need for von Neumann.
No. You can just take its closure and then it doesn't matter. You don't to be embeddable.
Right, yes.
You don't
so
need to close yourself to embed. The contrary. right? It's easier to embed without any closure.
So it's not right. So it's not necessarily closed, but you could close it and get a von Neumann
Okay,
algebra.
so you can use the tracial state to define a GNS representation. So then you not necessarily embed in BH, but at least you have some representation into BFH, and then you can take your closure, and then you are a finite von Neumann algebra because you have a tracial state and you are closed in the weak operator topology.
Okay.
Okay. Okay, so at least I hope that although it was a bit, there were many details in this introduction of cons embedding problem, at least you have the flavor of the connection, and this is the important part, the point. The connection between being embedded in some algebra and being approximated using epsilon representations. So we saw that there is this connection in one way. Hyperlinearity implies being embedded in this thing, but my point is that the other way around is actually easier and not harder. Great. So let's take a break, and I'll just say that after the break, I'll talk about
but what is the answer?
how can you use games to show that the in particular is wrong. So we are going to show that the in particular is just wrong, and thus the cons embedding problem is just not true. So the answer to not true. The answer to this question is just no. And we will use games, and I will explain how this is done. At least the theorem that needed to be proven.
And this is done explicitly?
Yes, not the most explicit way. I'll explain what do you get and how explicit is it and how not explicit is it. So you get some finitely presented algebra. You will get some finitely presented algebra, and I'll explain how to generate from it a separable finite von Neumann algebra that does not embed into R to the U. Okay?
Mm-hmm. Okay.
Okay, so let's take a 10 minutes break. So we'll meet again in 5 or at 5, okay?
Okay.
Sorry, Michael, so just your last comment, you mean you will be able to generate such an example given some properties of the game?
Yeah, I'll say that given that a specific game can be constructed with some properties.
Yes.
An algebra connected to this game must have a tracial state. Thus, it has a GNS representation. Okay. The closure of this GNS representation is a finite von Neumann algebra that is not embeddable inside R to the U. This is what I'll say.
But what's not clear is whether such games exist.
Yeah. The fact that these kinds of games exist is a corollary of the refutation of Tserelson's problem. So the no answer to Tserelson's problem.
I see. Thank you.
You're welcome.
By the way, Naki, I remember you asked a question about, yeah, it's kind of indirect, but in some senses, for cons embedding problem to be even interesting, the Hilbert space we constructed before has to be inseparable.
Okay.
Yes.
Oh, so that also answers. So you have to go by the way that Alex, so by something like this.
Yes, because I mean there are some deep, like essentially if you look at cons embedding's conjectures formulation here, it asks whether R to the U is universal in some sense.
Yes,
right? Like,
exactly. That's, yeah, I was wondering, Michael, why didn't you say this? That's somehow the most elegant way of saying the problem. That R to the U is universal. You can, it swallows everything.
Exactly. And there was a deep, I don't know for sure when it was proved but a very beautiful theorem of Zawa, where he showed that there cannot be a von Neumann algebra which is universal in this sense that acts on a separable Hilbert space. I mean, so any such universal construction has to come from an inseparable situation.
Okay. Okay.
So
swallowing all separable finite von Neumann algebras must be something that acts on a non-separable Hilbert space.
Yes. Yes.
Must be
So
the-
does
I haven't seen. Mhm.
So does it answer the
Big
question of
monster,
Alex
yeah.
from before?
So Alex asked. Alex had
So
a more
deduce,
specific.
Alex.
I mean, Alex had a more not basic, but concrete question about. Yeah, just ultra product of finite dimensional Hilbert spaces. I mean, I'm pretty sure it's also inseparable, but it's not this requires some explanation, which I don't exactly remember right now. But yeah.
So even if it's an ultra product of finite spaces, it's still non-separable.
I think it's inseparable, but don't take my word for it yet.
I think. Thanks, Nati. This is good.
Anytime.
I'll use it again.
Sure.
Cool. So now, as I said, we want to give some connection between games and their properties, specifically their quantum value and other values with respect to other correlation sets that we talked about last time, and some properties of some algebra. And the way we do it is that we first restrict the family of games to a specific set of games called synchronous games. So what is a synchronous game? A synchronous game is just a game for which the inputs to both players are the same. The input sets of both players are the same. The output sets of both players are the same. So we just have I and O instead of IA, IB, OA, and OB. And for every specific question, if I send both players the same question, they need to output the same answer. Okay, so this condition states that if you asked both players the same question and they replied with different answers, then this is a losing condition. Okay, so this is not such a restrictive requirement of a game, but this is our requirement. We will see that in some senses, synchronous games act nicer than general games. Okay, great. Now we can define for a synchronous game the game algebra of it. Okay, so how do we do that? We need generators and relators, right? So our generators will be just for any question and answer, we have a single generator, okay? And the generators are all projectors, so they projective operators, so they are the square of themselves and they are self-conjugate. They sum up, so for every x, the EXAs sum up to the identity. So you can see that these two conditions together, the fact that the generators are all projectors and that they satisfy this condition, is exactly what we asked of a projective valued measure. So up until now, for any x and a, we get these generators and they come in clumps in sequences that are projective valued measures. Great. And the last set of relations that we need to add is that if the XYAB is a losing condition, the product of the projectors EXA, EYB is equal to 0. Okay? And this, maybe I need to, no, everything is symmetric here, right? So it's okay that I wrote only multiplication on the right. It's the same if you multiply it from the left, okay? Okay, so this is you agree that this is a finitely presented algebra, and every synchronous game defines this kind of a finitely presented algebra.
Michael, do you need, in the end, it should be V of A, B, X, Y in the end?
Yeah, if I wrote it, yeah, maybe I wrote it the other way around. Yeah, I mean, consistent.
Yeah, it's right. In the previous item, it's
yeah. Thanks. Hopefully I'll remember it. If someone will send me an email that I need to fix it, I will remember. Thank you. Okay, anyway, but the point is the same, right? That if whether I write the questions on the left and the answers on the right or vice versa, I don't remember what I did last time, but here in the same slide, I do it in two ways. So this is clearly wrong.
But by the way, I think you do need to write both conditions also, because
maybe I do. I'm not
I don't see
sure.
that you don't. I don't see that you don't.
Which two conditions?
The last one. Oh, you also need to write EBY.
Maybe I need to write also that
EBY times EAX.
Maybe I need to let's just say that maybe I need to assume this as well. But the point is that there is some finite presentation. Maybe I need to add that EBY EAX is also 0. I'm not sure right now. I need to check that. Maybe it comes. No, I'm not sure. Maybe I need to.
Okay, but the moral of that is that this gives you
an algebra, a finitely presented algebra. So any synchronous game defines a finitely presented algebra.
But you didn't use the fact that it's synchronous so far. This
I did because I took only generators of the PVMs of one of the players.
Okay,
right?
but you didn't use this.
So in
the
some
condition
sense, I assume there is a hidden assumption here that the strategy of the left player and the strategy of the right player are the same. Okay, in some sense. I think this is a hidden assumption here. And
then you don't need both sides.
Yes,
maybe
symmetric, then you don't need
both sides because it's
yeah, but I didn't say that the V is symmetric.
These are projections. Right? I mean, same projections are.
Right. The fact that they are projections means that this is just the intersection. Okay, so this is just the intersection on the right. Thanks, Alon. This is just the projection on the intersection of their image space. So being 0 on one side automatically it gives you being 0 on the other side. Thanks.
That's true if they are commutative.
Right, and they are not. Okay. Okay, you're right, Paunes. Leave you.
Okay,
sorry.
But maybe we should start with the end. The end is that if you have a representation.
If you have a game, you have an algebra.
Sorry.
This is the end is that if you have a game, a synchronous game, you have an algebra. This is the point. Maybe
no,
I'm
but there's
missing
more
this
than
condition.
that.
Maybe I'm not. But the point is that you have an algebra.
Yeah, but
and
this algebra, the reason you defined it is because if you have a good representation of it, then you have a strategy.
Great, this is the point. Having a finite dimensional representation of this algebra is the same thing as having a perfect quantum strategy of this game. This is a great, we constructed this, you are very right, Guy, and this is the next slide. Having a finite dimensional representation of this algebra is the same as having a perfect quantum strategy for your game. But the question is there a connection between having perfect quantum commuting strategies or quantum approximated strategies? What is the connection between representations of this algebra and perfect strategies with respect to other correlation sets? So what Guy said right now is quite clear that at least for finite dimensional representations, having a finite dimensional representation is the same as having a perfect quantum strategy. But we will see in a moment that other properties of the representations of this algebra implies perfect strategies in other correlation sets. Okay?
No.
What yeah, you are trying to say something? Huh? Dorit?
What did you say? You somehow mentioned also commuting, but can you say it again what you just said?
Yeah, that there is a connection. The next slide. Maybe I'll go to the next slide. Yeah, making hard time for myself. The point is that having a nice representation of this algebra, let's call this algebra AG. Maybe I didn't write it in the previous slide, but AG. Whoa, what happened here? Okay, AG is just the algebra from the last slide. Great. Okay, so the point is that there is a connection between representations of this algebra and having perfect strategies with respect to specific correlation sets. Okay, so Kim, Paulson, and Schaffhauser proved in 2017. This is actually based on previous results of Cleve, Mittal, Vidic, Slofstra, and actually others. But they showed it not for general synchronous games, but for a specific subset of synchronous games. And Kim, Paulson, and Schaffhauser somehow generalized this result. And they proved the following, that this game has a perfect quantum commuting strategy if and only if this finely presented algebra has a tracial state. The second thing that they showed, that it has a perfect quantum approximating strategy if and only if it has any homomorphism of unital algebras to the ultra power of the hyperfinite to one factor into R to the U. So any homomorphism that sends 1 to 1 automatically gives you a perfect quantum approximated strategy. So any representation of AG inside R to the U will give you a perfect quantum approximating strategy. And as Guy mentioned, okay, and he noticed that, and I said this is the easiest part, so 3 is almost by definition. If you have a finite dimensional representation, so any homomorphism into M and C, you have perfect Q strategy, and this is vice versa. Okay, but we said, our in particular said that we think that if you have a tracial state, then you have a GNS representation, so you already have a homomorphism into B of H. And this means that having this can be, from this you can deduce that if you have a game with perfect quantum commuting strategy and no perfect quantum approximated strategy, and you actually construct this game, the finitely presented algebra AG refutes Cohn's embedding problem.
So now you're talking about strategies which are infinite dimension or something.
Quantum commuting is the model where we had a single Hilbert space that can be infinite dimensional, right? And but the operators of the two players need to commute with one another.
Yeah.
Not inside the player, but between the players. This is the quantum commuting model, right? And the quantum approximated is just the closure of the quantum strategy. So this is the closure of the finite dimensional space set.
So can you remind what do you mean by perfect strategy?
Value 1. Never loses. A strategy that never loses. Yair, you had a question also before.
Same question I wanted to ask. If perfect means you are surely winning. That's
yeah. Perfect, surely winning. A correlation that gives you value 1 in the definition from our previous talks. Okay, so what Jean, Natarajan, Vidic, Wright, and Yuan did is specifically construct a game whose quantum commuting value, so they show that there is a game, there exists a synchronous game. Wow, I don't know why my computer is so, it's very stuck, I don't know why. Okay, so there is a game which is synchronous. Wow, it's just.
It's like, in the old days you had the chalk that you couldn't hear on.
Yeah, but with the technology, you assume that it should be better, right?
Modern analog of this, yeah.
I don't know why, but my computer runs very slowly, and also my iPad, probably they are uploading or downloading something which is too hard for them.
Looking at the running processes helps.
Yeah, okay, so maybe I'll do it in a moment. I think for now this will suffice. Okay, so there exists, what they proved is that there exists a synchronous game such that its quantum commuting value is 1, which means it has perfect QC strategy, but its quantum approximated value is strictly, it's smaller or equal to 1/2. Okay, so it's not strictly smaller than 1/2. They don't know the exact value, but they can show that it's smaller or equal to 1/2. Okay, so this just means that if you take, they don't know the size of the actual representation. They say that very coarse approximations says that it has 10 to the 20, at most 10 to the 20 generators, okay, and things like that. So they did like back of the envelope calculations, and they say that it's probably quite a huge representation. But this game, you can follow their paper, you can potentially write down this representation, and then this algebra has a tracial state. You take the GNS representation of this tracial state, you take the von Neumann closure of this GNS representation, you get a finite von Neumann algebra, and this finite von Neumann algebra, not only it is not embeddable in R to the U, it has no homomorphisms into R to the U. It's a strong refutation of Cohn's embedding problem, okay? Okay, let's take a few moments to let this sink in, or maybe, I think this is a good point to talk. So take a few moments and then we'll discuss this point.
So just to understand, how I mean, is this as bad as it gets, or could it potentially, oh yeah, of course you can hope to reduce 10 to the 20 to 17, but is there, I mean.
Yeah, there is another point. Nati, that's a good question. If you know that your tracial state is faithful, it means that actually your original algebra can be embedded in the bounded operators of some Hilbert space, and its closure is not embedded in R to the U. Okay, but so you can have a finite finite presentation of an algebra such that the algebra itself is embedded in B to the H, and its von Neumann closure is not embedded in the right way. But here you have a quotient. So here we have a potentially a quotient of our finitely presented algebra, and this quotient is not Cohn's embeddable. This is what actually is shown here. So maybe a better thing will be an algebra with a faithful tracial state.
Michael, can you go back to the previous slide for a second, that we will see again what's the precise definition of A of G. So A, G is a game. You have a set IA, set P, and every X in A.
Michael, is there some condition on the game? Like, okay, this theorem translates conditions on the game and the game to the game algebra, but is there some condition on the game which gives a faithful tracial state?
I'm not sure. At least as I see it, no. Like, the fact that you have perfect strategies does not imply any faithfulness. And this is why they get such a strong refutation, actually. So yes, I at least don't know of a condition. Maybe you can change the value with some other condition and maybe get a faithful thing. I'm not sure. I don't see why you should have such a thing, because
so Michael, these CHSH,
you can lose information, right? What?
These CHSH games, they're the building blocks of these examples?
We said last time that the CHSH doesn't have a perfect quantum computing strategy.
No, I wonder.
So in some sense, they are problematic. So there's something that replaces it called the magic square game. Paris-Mer means magic square game, which has a perfect quantum value, and you can somehow use it via something called self-testing. And I thought before the talk that I will be able to talk about a bit about self-testing today, but the time will not allow it probably.
Yes, but just this magic square game is a textbook. It's almost as simple as the CHSH game. It's something that goes into exercises in quantum computing. This is not where the complexity arises.
No, fine. I just ask, it's I see the pyramid and I ask, is it made of wood or brick or what?
I wanted to ask also, so their proof actually goes through, not through the cons embedding problem, but actually through Tsearelson's problem, right?
Yeah,
I mean, what
this
they
is
actually
true.
do is they actually construct a refutation of Tsearelson conjecture, right?
Yeah, exactly. But what's nice is that there is a different way of saying that disproving Tsearelson disproves cone. But,
yeah, I know it's equivalent.
Right, but here you have a very straightforward connection, right? Or I think this is a nice presentation exactly because now I can tell you there is a representation of a specific algebra that you can deduce from if you go through the game, and this algebra has the desired property. So I don't want to exaggerate and say that it's a direct construction because, as we said, this is an algebra whose one of its quotients is not cones embeddable. It's not hyperlinear.
But it does give you a recipe.
No, the algebra itself is not hyperlinear, but the point is that it not necessarily embeds in any B of H, right? The algebra that they construct. It has a GNS representation, but it doesn't necessarily itself embeds in any B of H.
So, but it's constructive to find its quotient that doesn't?
I'm not sure how, this is a question about GNS representations. I'm not sure how constructive this part is, right? So the fact that you use a non-faithful state means that you are when you move from the finitely presented thing into B of H, you lose, it's not an embedding, it's just a homomorphism. So I think this is the only point in which you can say that this is not as a real, a straightforward construction, explicit construction, right? Yeah.
No, Avanti?
We have a question from the chat. Maybe you answered it already, but Hagai asks, if some construction works, can you show there is a synchronous game that works?
I'm not sure. Maybe you can synchronize. There are games. Okay, so synchronous games have some good properties. For example, if there is a quantum spatial strategy which is perfect, automatically there is a quantum strategy that is perfect. So these kinds of properties are known to not hold for all games because there is a separation between the quantum strategies and the quantum spatial ones, like there's quantum correlations and quantum spatial. This is a result of Colodangelo and Stark. But I'm not sure if for this specific methodology you can synchronize or not. So maybe there is a method, but I don't know of it, of generating a game which is not synchronous and then doing some magic and making it synchronous with the same properties.
Yalla.
Okay, great. So we move along. Okay, I understood. Yalla, I understand.
Everyone does.
Okay, so let's talk about what is compression and why does it imply RE is included in MIP star. So we go back to more computer science complexity things now. And for us, the goal is to show a reduction from the halting problem to deciding whether a game has value 1 or half. So just a moment. To do that, I need to first explain how to generate a sequence of games in a uniform way. Okay, so in computer science, there is this notion of uniform generation, and here we want to generate a uniform sequence of games, which just means that we want a single Turing machine to have the property, so a finite being, a Turing machine, have the property that if you input a number, it outputs so if you input n, it outputs the nth game in this sequence, okay? And let's recall the following. So what is a game? A game is 4 sets, so we need to explain if you want some, if for any input n you need to output a game, you need to explain to me what are the sets. You need to explain to me how to sample the probability mu of the probability over IA times IB. And you need to explain to me how to evaluate the winning predicate, the function that for any quadruple decides whether this is a winning condition or a losing condition. Great, so the definition of this uniform sequence of games is called a verifier, and actually it consists of 2 Turing machines. And we ask that these 2 Turing machines are polytime, but now I need to say exactly what does it mean polytime in this scenario. I mean that S and D run in at most n to some lambda times some constant for a fixed C and lambda. So we fix beforehand 2 constant, C and lambda, and I claim that our 2 Turing machine, S and D, that I will explain in a moment what do they do, both run at most C times n to the lambda steps. Okay? Okay, so this S is called the sampler, and what it does is the following. It flips some finite amount of coins. Okay, so it takes the uniform distribution on some F2 vector space, so just finite strings of bits of a fixed length, and from that it calculates 2 questions, X and Y, that comes from, okay, so for at least for now, I take X and Y to be any string of bits. Okay, so at least for the moment, IA and IB are infinite. Okay, but this will be fixed in a moment. But the point is that this Turing machine gets as input. It doesn't get as input. You just tell it to flip some coins, and then it do some processing. The processing time depends only on the n that we started with, and it outputs 2 questions. Okay, and it does all of this in at most this amount of time. Great. So this is S. What does D? What does D do? Okay, this doesn't sound good. So Dn, you just give it 4 strings of bits, X, Y, A, and B, and it needs to decide whether it's a winning condition or not. And I will say the following. If it halts and outputs 1, this is a winning condition. If it does anything else, either it doesn't halt in the correct amount of time or it outputs any other output, we said that this is a losing condition. Okay, this is the way I interpret the D. Okay, so if we have these 2 Turing machines, we can note that actually there is no
necessary. We can't assume that it stops in a finite amount of time and gives it.
We can, because we can tell the Turing machine to just stop after at most this amount of steps, at most C and lambda amount of steps, right?
Great.
And the fact that we did
I didn't understand the connection between n and S of n.
Okay, so S of n is a Turing machine that does the following. It flips.
So S of n itself, wait, S of n is a Turing machine or S is a Turing machine?
Okay, S is a Turing machine with the single input n, okay? For any n, S of n flips a finite amount of coins, and this finite amount depends only on n. Then it calculates some calculation that takes at most C times n to the lambda operations. And then it outputs two questions. What are the two questions? Just two strings, X and Y.
Okay.
Okay, so
But
this is
you
a
don't know the
sampling.
length.
What?
You don't know the length of X and Y.
Oh, so
Yeah.
now I'm claiming that the fact that I run at most Cn to the lambda time means that the length of X and Y is bounded by this number.
Oh,
Okay. So actually, this is what I wrote here. Actually, the questions and the answers cannot be longer. Any question and answer, okay, any question that can be sampled and any answer that can be read are bounded by 0, 1 to this number. Right? So we can just assume a priori that IA is equal to IB is equal to OA is equal to OB, which is just all the strings of length at most polynomial in N, and actually this specific polynomial in N. So we get, so my claim is that although I didn't give you the size of IA, IB, OA, and OB, we can assume that this is the size of IA, IB, OA, and OB, and this generates a sequence of games. Any question about this uniform generation of games? So it was a bit technical, but I think it should be quite straightforward. Okay, great. It was quite important, the fact that the only thing I let the decider do, the sampler do is flip coins, okay? That we push forward some uniform measure over some F2 vector space. Okay, so what does the compression theorem states? It says the following: given a nice enough verifier, so given such pair of Turing machines that satisfy some natural assumptions, okay? So the sampler behaves in some specific way, and actually the decider doesn't have many restrictions on it. We can generate efficiently a new verifier. So we get as an input these two Turing machine S and D, and we output two other Turing machines, S prime and D prime, such that, first of all, these two Turing machines are nice enough. So this nice enough property that I'm not saying what it is, but why doesn't it work? Okay. So this nice enough property stays after you do this operation. And you have the following property. So we stated that for any number, any natural number, we get a game. So let's call this game V2 to the N. So the game that you see here, I called it Vn. The game that we got here, we called it Vn. So this game has some quantum value. My claim is that if the quantum value of V2 to the N was 1, then the quantum value of V prime N is also 1. So this is the first claim. The second claim is that if the quantum value of V2 to the N was at most 1/2, the quantum value of V prime N is at most 1/2. Great. And the last part is a bit, it's both the hardest to show and maybe the hardest to understand. So if I denote by EGP, okay, so G is a game and P is some probability. EGP is the minimum dimension of a quantum strategy that can win with probability larger or equal to P. Okay, so for example, we stated that the CHSH game, if you want to win it, with probability smaller or equal to 0.75, you can use classical correlations, which just mean that you need zero-dimensional entanglement. Okay, so you don't need any entanglement. Okay, so CHSH, the E of CHSH 0.75 is 0. But we said that if you want to win the CHSH game with some probability, which is approximately 0.85, you actually need okay, you actually need two-dimensional strategy. So we defined what are quantum correlations last time. In the three previous talks, we talked about what are quantum correlations, and there is no one-dimensional or zero-dimensional correlations that achieve 0.85, but there exists a two-dimensional strategy that achieves that. So the matrices that we used in the POVMs are two-dimensional. This is what it means. Okay, but if you want to win, okay, so you can show that if you want to win with probability 0.9, you can't. So we said that the amount of entanglement is infinity. It doesn't mean that there is an infinite dimensional strategy that wins. It just means that there is no finite dimensional strategy that gives you this amount of winning probability. Okay, so this is EGP. If you want to win this game with at least probability P, you need this amount of entanglement. So you need the dimension of the Hilbert spaces that we used in the correlation sets in the quantum strategy to be at least d-dimensional. Okay, great. So the claim here, and now this is an important point, is that the amount of entanglement needed to win the nth game of V prime with probability at least 1/2 is bounded from below by the maximum between 2 to the 2 to the n and the amount of entanglement needed to win the 2 to the n game with probability 1/2 of the original verifier.
And n and lambda are the same for V prime?
What? Lambda is not appearing here at all, right?
Yeah, but I mean, do you still have some estimate on the complexity of V prime?
I still have some bound. I'm not sure. You maybe pay a price, so maybe C gets larger and lambda gets larger, right? The n is the input, so the C and lambda can potentially be larger. Yeah. But the nice enough means that you still have some bound on some polynomial time bound on the complexity of S prime and D prime. Okay, so let me at least give you the feeling of what happens here. The point is that if you have good quantum value, it stays good. If you have a not so good quantum value, it stays not so good, okay? And it gets harder, you need more and more shared qubits that are very entangled with one another to win with at least 1/2 probability. So it's in some sense, it's harder in the sense of you need more, resources? Yeah, thanks. So you need larger entanglement resources to win V prime. V prime requires more entanglement than V itself. Okay, great. So this is the compression theorem.
No, the statement, no, the statement doesn't make sense. I mean, in the following point, you transform one verifier into the other. So there are good news and there are bad news, and somehow this statement doesn't distinguish between the good and the bad new. The good news is
these are all good news.
Wait, a moment. The good news is that instead of having 2 to the n random bits, you only need n random bits. Is that correct?
Why do you see that? I don't see that. I just state that to win the nth game.
No, forget that. I'm not even talking about.
Talking about the first item.
Yeah, just the first item.
But both first.
Yeah, but the first item doesn't say anything about the entanglement. It doesn't say anything about the amount of.
No, I'm not talking about entanglement at all.
Just the sampling and.
He's talking about running time and
yeah. Okay. It says something about the fact that okay. So the running time gets exponentially better in some sense.
Reduce the number of random bits from.
Why random bits, Nati? I don't understand why the name.
So what? Maybe Michael, explain what is n again. N is not the number of random bits.
No, it's just the n is just the nth game generated by the verifier. We said that Sn and Dn define a game, right?
Yes, but the sampler uses the sampler and the verifier run in polynomial time. So
this is the correct point. If you think of V prime as simulating V2 to the V prime n, in some sense simulates V2 to the n. So in this sense, you get an exponential improvement in the running time. But this says nothing. The first and second condition says nothing about the amount of entanglement you need. It states something about
that's the point.
The connection between the values of games in different parts of the sequences, right?
V prime.
If you can win.
Michael, V prime is, let's look at this really from afar. V prime is a simulator of V. Okay. The first two items say that V prime is a good simulator in the sense that it agrees with V on what's a perfect success and what's a failure in the sense of value a half or less. Between a half and one, we say nothing, right?
Yes.
Okay. And so in what sense do we need a simulator? You can use the original machine. No. It's a simulator because rather than 2 to the n random bits, you only use n random bits.
It's not random bits.
Not random bits. It's complete computation altogether.
Computation.
It's right. Computation including random.
Sorry. It calculates much faster.
This is the point. This is the point.
Calculates much faster than V.
So these are good news also.
These are good news. The bad news, and somehow you put the bad news and the good news together. No, let's separate them. And the second part says, however, so there should be some however. In order to do this, you have to pay with entanglement.
But these are good news also.
Okay.
These are good news also if you want to prove
right. But in terms of simulation, the top part is good news, and the second part is,
okay, so you get time efficiency at the price of entanglement resources.
Right.
This is true.
Yeah.
You use more entanglement and you win with that time, the time complexity.
This is verifiers and provers. So you have a verifier and the provers. The verifier needs to work less. He saves exponentially. And the provers do the calculation for him by using more entanglement.
Okay.
Yes.
Without talking with each other.
Just
okay.
to make
What I'm saying is the second part should be however.
No, you shift the calculation part to the verifier, to the prover.
Okay.
You can put there, however, if you want.
Okay, thank you, David.
Fox News would put an however, CNN doesn't put an however. It's just a matter of point of view.
President-elect, yeah.
Okay, Liv, you give us your...
So just to make sure, the C and lambda constants for the verifier are the same as the initial... for the question, verifier are the same as with those for the initial.
Yeah.
You're not sure of the question, or
no, I'm sure about the question. I think that you cannot pay too large of a price because they do some iterative process, but I'm not sure like whether it's the same or whether they have some control of the way it enlarges. I need to think about it because
if they have no control, then the initial point on the fact that there is less computation is no longer valid.
Right. Yes. There needs to be some control, but I think that usually they just say something that there is.
I think it doesn't matter because instead of 2 to the n, it could be 1.2 to the n, and then probably you could get the same C and lambda.
Okay, so I will maybe prepare for next time this point, like what happens to the lambda that we talked about in the previous slide, because either it doesn't matter or it does matter and there is some bound because they get the following effect from out of it. So let's just say really quickly what is the reduction, and next time we will prove that this reduction works. So you do the following. You want to show that distinguishing between value 1 and value smaller or equal to 1/2 is as hard as deciding the halting problem. So you take a Turing machine. You define the following verifier over this Turing machine. The sampler, I tell you nothing about the sampler because the sampler depends on the fact that we use the compression theorem. But I can tell you something about the decider. The decider does the following. It simulates the Turing machine for n steps. So the nth decider, no matter what the questions x and y and the answers a and b are, it just simulates the Turing machine for n steps. And if the Turing machine halts, it accepts. So no matter what the questions and no matter what the answers are, in this scenario, it always accepts. Otherwise, the decider applies the compression theorem and calculates what would the compressed verifier would answer if it was asked n, x, y, a, and b. Now, this is a self-referential definition, but computer scientists are at ease with these kinds of things because there is a Kleen's theorem that states that this kind of thing has a definition. So this is well defined, although it's self-referential. And the point is that this verifier, okay, so I just stated that it is well defined, and we will see next time that
Michael, for this, don't you need as well that the previous slide was as itself recursive, that you can compute the derivative from the?
I stated that you can efficiently compute, can generate efficiently a new verifier.
Okay, I did notice that. Okay, yeah, that's the point.
The reduction upstairs in the previous slide is efficient. Okay. You should think of it as in the following way. You have a sequence of games. I give you the compression theorem. It generates a new sequence of games. Now, the way you define a game now is run the Turing machine n times, and then if it didn't halt, play the compressed game with the verifier, with the players. You should think of it as something like the following. Run the Turing machine n times. If it didn't halt, simulate a running time of 2 to the n times. If this one didn't halt, simulate a running time of 2 to the 2 to the n times. If this didn't halt, run a simulation of 2 to the 2 to the 2 to the n.
But it never depends on
everything.
It never depends on x, y, and b, right? Or
okay, so it does depend on x, y, a, and b because the compression theorem generates x, y, a, and b. So the compression theorem generates a game. So the first iteration does not depend on any game. It's just a running time of the Turing machine. But when you compress, it automatically generates questions and answers. And this is where x, y, a, and b gets into the picture. Okay, so quite amazingly, this kind of thing is possible. And we will see, as I said now, like if the Turing machine, the game that actually has value 1 if the Turing machine halts, and has value smaller or equal to 1/2 if the Turing machine does not halt, is exactly VM1. So the first, if you just input 1 in the sampler and the decider, you get a game. This game has value 1 if the Turing machine halts, and has value smaller or equal to 1/2 if the Turing machine does not halt. Okay, so if you want to stay around and let me spoil the beginning of next talk, you can. If you have any questions about what we've done up till now, we can also talk about it, but I think we are done.
Thank you.
Bye-bye.
This machine.
Bye. Thank you.
Thank you.
Bye. See you next week.
Okay.
Yes.
So
Yes, they
DM
are.
actually either accepts or just doesn't stop, right?
No, this doesn't. This is not what happens. This will always terminate, and this is part of the self-referential theorems in computer science that lives inside, like in the back of our heads here. So actually, V1 of M is a finite thing, and it calculates everything in a finite amount of time. And the point is just that, in some sense, there is some fixed point. There is some fixed point argument that states that you actually get something finite that terminates always in this case. So if you could have distinguished between the value larger or equal to, so 1 or small or equal to 1/2, you could have decided whether every Turing machine halts. And this V1 of M is just a finite game. So this is a game. Okay, it's a finite entity. It doesn't have, and everything runs in polynomial time of the index, the subscript index. So in this case, this is just a constant thing.
So you're saying that this D that you defined runs in polynomial time?
Yeah, DMN runs in poly n. This is what I claimed before, right? And we stated this polynomial was Cn lambda for some lambda and some.
No, sorry. Yeah, I'm not talking about this D. I'm talking about the D that you just defined, which like uses all the Ds.
My claim
together.
is that this VM is what I called nice enough.
Which
okay?
means
that SMN and DMN ABXY or whatever, the way I route it, XYAB or ABXY, both of them run in at most this amount of time.
Guy, I'm not sure what you call polynomial time. Polynomial time in what?
So I claimed now polynomial time in N with no respect to A, B, X, and Y.
Polynomial time in N, but the decision, it's not, I don't know if it's polynomial time in a description of the Turing machine. It might be logarithmic, even log time. I don't know. I really don't know.
Okay, wait, but okay, let's forget about the running time. This is a game with, this is an
okay, this is a
game.
uniform sequence. This is a uniform sequence of games, first of all, right? It's not a single game, it's a uniform sequence of games.
But at the end, you generate just one game.
Yeah, the point is that if you take the first one in the sequence, it already satisfies what we need in our proof. So it already proves that MIP star contains RE, the first instance.
Michael, I'm confused about one thing. Why do you need the exponential increase? I mean, could you have done well enough with the compression, which just, I don't know, goes to quadratic?
I think, I'm not sure. I saw that the authors claimed that you don't need exponential, but you need some improvement. And I'm not sure whether polynomial, I'm not sure whether polynomial improvement is enough.
So
but
where
maybe
is it? Where is it in the proof that you actually use that it goes fast enough?
No, here I didn't use here you can just say even that if I just wrote here V of n plus 1 and V of n plus 1, it would be enough.
So
replace 2 to the n by n. I think just this is what happens in their theorem.
Okay, their theorem is stronger than what you need in order to do what to imply the RE in MIP star. That's what you're saying?
Yes, like if you yeah, but the running times, I need to think.
I mean, the running times don't go into the RE inside MIP star, right?
No, but they depend on the subscript, right? So when I write F,
you need the sum, somehow the sum of the series of the running times to go to some finite number. Is that like the?
No, this cannot. What? I don't understand. Series of what?
Well, you get No, you run
My
it.
claim is that this is a game. Like this is a finite being. Like you don't need any series. You don't need nothing.
You really need an improvement, because if you allow some polynomial, larger polynomial in the simulating game, then and you just go from n to n plus 1, you're actually lost. So.
Sorry, if you go to n, why are you lost? I didn't understand.
Because you might allow slight, if you allow more time, so you're not doing anything faster. You're moving from n to n minus 1, but you change.
Oh, you just restrict the polynomial, so you need some super polynomial. That's what you're saying.
Yeah, I suppose.
Okay, so at least at some points of the proof, they stated that they need super polynomial. If I just state this compression theorem, and I didn't talk about running times, I think that, Dorit, your first impression is correct. Like Henry UN introduced at the IAS this theorem with only saying something like n plus 1, but he totally hided all the complexity of the verifier things. So
but we don't care for the matter of, for this,
yes,
implying the RE is in MIP star, this would be enough.
Yeah, but the fact that you stay nice enough is actually goes away if you only say n plus 1 or something like that. But if you don't care about being nice enough after compression, I think it's okay, and you can deduce the RE.
No, but you do care. I mean, the whole point is that.
Right, you do care. This is why I think they add the 2 to the n. Like the fact that the running times is important here. It's not it's not unimportant. But if you just want to do some kind of an induction, like I did here, saying that okay, if it runs t steps and n is larger than t, it has value 1. This is clear. But also, if it's t is between n and 2 to the n, you just use the induction once, and you deduce that the value of this game is 1. And if you do something between, if n is like even smaller than log of t, you do the induction twice, and so on. So there is some induction here. And the induction could be done also if it's only one steps. And this is what Henry is doing in his talk. But I think he's lying a bit, because he loses, the compression technique does need to do something like maybe not an exponential, but like Michael said, super polynomial improvement.
Okay, great, thanks.
So just one like very technical, trivial question. The game that you get, the inputs and the outputs, they're infinite. Am I right?
No, they are bounded by some like they are strings that are bounded by some polynomial, and you can say something about this polynomial. You can probably do a back of the envelope calculation and give me constants and say the game v1 of m is bounded by some function that depends only on m, and you can say something about this function, like
so
because you're running this, you're trying something, and if it doesn't work, you're trying another pair of simulator and whatever these decider.
Yeah, this is not true, because here I wrote only one time, right? So you just need to calculate dm prime of nxyab. I don't tell you what happens inside dm prime nxyab. You are correct that potentially this dm prime nxyab simulates another compression, but I didn't say it. I just said it compresses itself and calculates. And the point is that there is some fixed point of this like this Kleen's theorem that says that although this is it can be an infinite loop, it is not an infinite loop in this case.
Okay. Okay, thank you.
Cool. You're welcome.
תודה, להתראות.
ביי, מיכאל. בכיף.
Bye. Thank you.
Bye, Gulnara. Thank you for coming. Okay, I think I'll shut down the meeting. Bye,
Thanks for
Theora.
the seminar.
Bye, Livio.